Very good. Thank you very much, Tony. As Tony said, my name's Robert Leese. I'm Chief Technical Officer at the Smith Institute. I'm delighted to have this opportunity of giving you just a little glimpse into a piece of work which, without doubt, is one of the most exciting projects that I've ever been involved in. I should also say in the hall this afternoon is Jakob Blavant, who's our Director of Mathematics. He was also part of the project team. The purpose of our work, quite simply, was to reshape the telecommunications sector in the United States. And this diagram, I hope, gives you some idea what that means. So what we have here is a chart showing all the radio frequency allocations in the United States as they stood in about 2016, a couple of years ago. The low frequencies are at the top, and the higher frequencies are towards the bottom of the diagram. And they represent all the devices and services which in some way use the radio spectrum for wireless communications. What I've done is to highlight a few blocks of spectrum, in particular those blocks which are used for television broadcasts. And the reshaping that I referred to, the reshaping involves repurposing some of that TV spectrum for use by mobile data carriers. And this is in response to the continually growing demand for mobile data capacity. As you can see, the spectrum is very congested, and there isn't really any way of accommodating new services without making changes to existing ones. So the devices that we're going to be really talking about in the back of our minds are smartphones, tablets, those sorts of things, which are the devices that we use to transmit and receive mobile data, and also television. There are many other radio devices. You'll be familiar with many of them, I'm sure. They're all represented somewhere on that chart. I won't say any more about any of them other than to say that baby monitors certainly look more sophisticated than the last time I had to buy one. So, what I'm going to do over the next few minutes is to say something in general about the challenges of managing the radio spectrum. I'll say something about the approach that was used for repurposing TV spectrum in the United States. That's a mechanism that became known as the Broadcast Incentive Auction. Say something about its implementation and the innovations that were involved, and then draw some conclusions. Our customer in this work was the Federal Communications Commission, based in Washington, D.C., and they are the national telecommunications regulator for the United States. So the equivalent organisation here in the UK would be Ofcom. And the telecommunications regulators around the world have similar sets of responsibilities. So in particular, promoting competition in consumer markets. To do that, they need to make spectrum available for new uses, and they also have to ensure what's called cross-border harmonisation, which in plain language means making sure that your mobile phone works when you go abroad. They also, and this is very important, need to protect incumbent users. When the spectrum is so congested as it is, there's very real risk of interference between devices and between services. And the regulators have a crucial role in protecting incumbent users and ensuring that there isn't unnecessary or unwanted or even illegal interference. And finally, this I think will come through in the work that the FCC have promoted on the Broadcast Incentive Auction, they need to innovate in spectrum allocation mechanisms themselves. Just to say something also about the Smith Institute's work in this area, our work has really grown over the last 10 years or so, and it's grown in step with the growth of auctions as a preferred mechanism for spectrum management. And the high values involved in radio spectrum have themselves driven innovation in auction design. So our work started actually here in the UK with Ofcom, which is an innovative regulator itself. And then from there, we managed to get opportunities to work in the rest of Europe, and also in Australia, Canada, and now in the United States. The Broadcast Incentive Auction itself opens a new chapter in spectrum management mechanisms. It's the world's first two-sided spectrum auction, and we'll see in a moment exactly what that means. Let me take a closer look at these TV channels. So this is the part of the spectrum which was towards the bottom of the diagram that I showed earlier. It's what's called UHF television channels. UHF stands for ultra high frequency. There's also a band at slightly lower frequencies than that called the VHF band. That stands for very high frequency. Now, it turns out that the TV channels in the current allocations occupy the most valuable part of the radio spectrum, what the Americans call the beachfront property. And it's called beachfront property because it balances the dual characteristics of coverage and capacity. So lower levels capacity is reduced, and at higher frequencies coverage is reduced. But in the TV band, you've got this very nice dual purpose, and in particular, those frequencies are very much sought after for in-building penetration of signals. What I've shown at the bottom of that of this slide are the possible outcomes of the broadcast incentive auction. So the status quo is represented there by the top line in the diagram. The light blue squares running all the way across represent continuing use of the whole band for TV. But there are also a range of possible other outcomes which may have emerged in which different amounts of spectrum are repurposed for mobile data. And those are represented by the green blocks in the lower parts of that diagram. And as you can see, there are different amounts of spectrum that could end up being repurposed. The actual amount of spectrum that was going to be repurposed was itself part of the solution. That wasn't fixed in advance. It was determined as part of the broadcast incentive auction mechanism. What is the real driver behind this? The amount of growth in demand for mobile data is about 50% annually and doesn't show any signs of slowing down. If there's no more spectrum available, we need to find it from somewhere. I should also just briefly say something about the yellow block of spectrum in the top part of that slide, which is the same as the red part in the bottom slide. That is one TV channel's worth of spectrum, and it is used for radio astronomy. It can't be moved. It just happens to be in the middle of the TV band and needs to be worked around. What I have now is a short video explaining the broadcast incentive auction process, which was put together by our customers at FCC. So let's see if I can make this work. Yeah.
How does the incentive auction work? First, a reverse auction determines how much it will cost to repurpose a given amount of spectrum previously licensed to television stations. TV stations are offered money to vacate their spectrum. Stations that do not sell are guaranteed a channel in their current frequency band. The reverse auction starts with high prices offered to TV stations. If more stations accept these prices than needed to clear the specified amount of spectrum, prices decrease. As prices drop, some stations will reject the prices offered and join the set of stations that will remain on the air. If no spectrum is available for a station, the price offered to the station stops decreasing. The auction continues until there is no spectrum left for any of the stations accepting the prices. This establishes the amount of money needed to clear the spectrum. Next, the same amount of spectrum is offered in a forward auction to wireless carriers. In the forward auction, prices start low and rise until the amount of spectrum for which there are bids equals the available supply. If the amount bid by wireless providers is not enough to pay the broadcasters, then the auction continues to a new stage, in which both the reverse and forward auctions are repeated starting where they left off. In each succeeding stage, the FCC designates a smaller amount of spectrum to be sold to wireless carriers, and therefore needs to buy fewer channels from TV stations. Because this frees up more space for TV stations, competition among TV broadcasters makes their prices go down. And then in the forward auction, less wireless spectrum for sale means more competition among wireless bidders, which increases the price of the spectrum. The incentive auction continues through as many stages as are necessary for money bid by wireless providers to pay the selling TV broadcasters. At that point, supply and demand are in balance and the auction ends.
Okay, so I hope that gives you at least a flavour of what a two-sided spectrum auction is all about. We have the TV broadcasters who are sellers of spectrum and mobile carriers who are purchasers of spectrum. And the broadcast incentive auction is a way of making that market work. I can tell you that the outcome of the incentive auction was concluded in 4 stages rather than the higher number that might have been anticipated in the video. And it resulted in a repurposing of spectrum such that all the spectrum in the TV band that is below the astronomy channel is retained for TV, and all the spectrum that sits at frequencies above the astronomy band has been repurposed for mobile data. What does that mean in numbers? Well, there are 14 blocks of spectrum which have been made available now for mobile data. Those are the green squares in the previous slide. And they are released on a geographically regional basis in the US. So there are 416 what are called partial economic areas. And the licenses for spectrum exist individually in each of those areas so that carriers can assemble the groups of licenses that they need to provide their particular service. The total amount of money paid for these new licenses was $19.8 billion. 50 mobile operators acquired new spectrum as a result of this process. The amount of money that was needed in order to free up that spectrum, in other words, the amount that needed to be paid to the TV stations, was $10 billion, and 175 TV stations received financial payments as a result. So these were stations that took money to either move to the VHF band, in other words, move out of the UHF band entirely, or in some cases they elected to go off air completely. The stations that remain in the TV band, in the UHF band, they may be repacked, so there may be some reorganisation of TV stations within that band. So not all of the stations who stay necessarily stay on the same channel. In total, out of about 3,000 TV stations, 987 will move channel. Some will share a channel, and this was reflected in their bidding activity, and only about 12 stations will actually disappear. And those are stations who are going off air voluntarily, having accepted the offer of a financial incentive to do so. Say something about the challenges involved in making all of this work. I mean, first of all, the approval of the process itself required legislation in Congress and was not a rapid process. It also needed international agreements with the governments of Canada and Mexico. As well as engaging with governments, winning over the confidence of broadcasters and the mobile operators is absolutely crucial. When auctions fail, they generally fail through having lack of participation. They're absolutely crucial to get good engagement. And that was done in large part through the auction design and in making the bidding experience as simple as possible for all participants. Behind the scenes, there's a lot of groundbreaking technical challenge, and I'll mention some of those challenges in a moment. The key thing about all of them was the solutions that we came up with had to work right first time. Once an auction started, it can't be stopped and restarted. At the system level, you can think of the broadcast incentive auction as really having 3 components. There were the bidding systems, which were highlighted in the video. There are a lot of optimizations which go on. The optimizations are used for the repacking that I talked about, and also for deciding how much spectrum to try to release at each stage of the auction. And there's also a lot of constraint modelling that goes on in order to make sure that the interests of incumbent users of spectrum are protected. Remember, that was one of the key roles of the FCC. Another challenge was the auction schedule. So the launch date, the start date of the auction, the date on which bidding would start, was announced many months in advance by FCC, way before most of the systems were even in prototype form. So that concentrates the mind a little bit. As far as the skills were concerned, the FCC assembled a hand-picked task force which combined FCC's own staff with a group of about half a dozen specialist contractors. As far as I know, we were the Smith Institute was the only contractor who was engaged from outside of North America on this project. Our role was severalfold: to validate all the algorithms and optimization models, to provide an audit of all the algorithms for both accuracy and speed, and very importantly, for system integration testing. As you might imagine, when you've got a complex system with many components, when issues arise, they very often arise at the interfaces between components, and that was our responsibility to track those down. We had a team of 6 people working on this over a period of 18 months. I'll say something about the challenges. On the left here, you can see, I think, on the right part of that panel, a blue dot. That's a TV mast. And the other dots show the coverage area of that TV transmission. Each green pixel there represents a 2 kilometre by 2 kilometre cell in the US. And so the populations of all those little cells represent the total coverage population of that TV station. That was all taken from radio propagation models and from census data. So there's a big data analytics challenge behind this as well. If we put another TV station nearby on a nearby channel, as we've done in the second panel there, so you can see the second TV station has appeared on the left, then there is interference in some regions, and those pixels that have turned brown are those that now no longer receive a signal. Now, all the broadcasters, as part of their guarantees for protection of incumbents, were guaranteed that 99% of their coverage population would be preserved. So this would be an unacceptable solution here. That translates on the right-hand side to an edge in a network. So the right-hand panel there has a node for every TV mast, and it has an edge where there is some constraint between pairs of masts. You can see that the interference graph, as it's called, extends north above the Canadian border, and that's because the Canadian TV stations were repacked as part of the process. There isn't any such extension south into Mexico. You may be forgiven for thinking there's a big wall along that border. In fact, there isn't, as far as I know. It's simply that the TV stations in Mexico were not repacked. They provided more of a boundary condition to the repackings going on elsewhere. Second innovation was the feasibility of TV assignments. So this was especially relevant in the reverse auction when TV stations are offered options and they have to select between options. It must be determined in advance that no matter what options are selected, there is a valid TV assignment always available. So there needs to be a lot of feasibility checking going on. If false positives in that process are absolutely catastrophic, that means you could run the process and find that there isn't actually a valid TV assignment available. False negatives, they're not catastrophic, but they can be very expensive. They can cost you $100 million if you get one of those wrong. It's also an NP hard problem, and you've got to solve it thousands of times. So there were some challenges there, and some new techniques were developed, effectively machine learning techniques, to learn the complexity landscape of that interference problem. Finally, optimal repacking. These are the optimizations that I talked about earlier. They not only make sure that the TV spectrum is packed as tightly as possible, they also maximize the quality of the spectrum that's offered to the mobile operators. There's certainly a high cost if the auction proceeds to unnecessary stages, and in those optimizations, any violation is a violation of public policy. So there's no room for being soft or otherwise flexible with the constraints. Let me just, in conclusion, come back to the criteria for the President's Medal and show how I think this piece of work meets all of them. First of all, demonstrable benefit. Well, the benefit for consumers is the release of spectrum which is going to address the increasing demand for mobile data. For the mobile industry, it will accelerate the rollout of 5G networks. What's the value? Well, in immediate terms, we've got $20 billion of value that's been released. Economic estimates of what the consumer surplus is means that over the next 10 years, the economic value will be measured in hundreds of billions of dollars. The intellectual and novel content, it's the first time that OR and auctions have been brought together in this way. The bidding systems, in particular, were used as a way of gathering information that can then be used in spectrum optimizations. The likely longevity, certainly over the lifetime of the new mobile licenses, which is 12 years. But also, the important thing is we now know how to do this. Spectrum is congested, there is no new spectrum, and so we're going to be increasingly looking for repurposing existing spectrum. This was the first major exercise in repurposing spectrum through a market mechanism. Finally, Very final point, the excellence of the OR process. As you can probably gather, highly multidisciplinary team alongside ourselves, work with economists, computer scientists, many others, lots of lawyers. You wouldn't believe how many lawyers you come across. Other thing to mention is the highly agile project management. I mentioned the fixed start date. We had daily scrums for raising and resolving issues, lots of mutual support within the team, absolutely crucial. And really, it was just a privilege to be involved in such a project that successfully delivered such an important piece of work. So thank you for your attention. I'll be happy to answer questions.
We'll go straight into questions again. Thank you. Alan, over to you.
Thank you very much for an excellent presentation. I was interested in the statement you made that OR is the key to connecting the auction processes, and I wonder if you could say a little bit about how you got the OR injected into what's obviously already a very complex setup.
So between at each stage of the auction, there needs to be a decision made as to how much spectrum to try to release, so what is going to be what's called the clearing target. And that is done by looking at what the currently stated preferences are for all the TV stations and working out how well they can be packed up and how much spectrum can be released as a result. And it's very possible that different amounts of spectrum can be released in different parts of the country because of the geographical distribution of the TV stations themselves. So that's really where the OR comes in. There's a successive set of layers of about 20 different policy objectives, which were all formulated as mathematical models in order to perform those optimizations between stages.
And the testing that goes behind the scenes to make that happen, if you could just elaborate slightly on that, because you say it's got to work the first time,
yes.
comfortable.
Yes, and that was very much central to our role. I think of all the contractors, we were probably the ones who had the greatest visibility of all the components in the system because we were the ones trying to break it, essentially. And so that was the way we approached our testing, was what can we come up with that we think is going to break this?
Thank you. John.
Yes, thank you very much indeed. I'd just like to clarify a little bit the role of the Smith Institute in the project, because you talked about having a validation role, but you also talked about some of the innovation around use of machine learning and so on.
Yes.
I'd just like to understand a little bit more what your team did versus the army of all the other experts.
Sure. So our central role was validation and testing, and in particular testing the components when they were started to be assembled into systems. We also had a responsibility to look at the algorithms that were being used and where we could find or that had been proposed and where we could see opportunities for improvement either in speed or accuracy, and we found examples of both. Then we were able to feed that back into the design process, work with some of the other contractors in the team in order to build those into the systems that was finally deployed. So we found some examples where there was conceptual gaps, which could have been catastrophic, and other areas where it would just have been the quality of the final solution that would have suffered.
Okay, thank you. Sonia?
Thank you very much for a very interesting presentation. Could you please tell us about the time scale of, let's say, one stage of the auction? How fast your algorithm needs to be?
Well, first of all, I should say the auction itself took a year to complete, which may come as a shock to many people who imagine an auction lasts a few seconds, people sticking their hands up. It went through 4 stages, as I mentioned. So you might think that the timescale is relatively long, and indeed some of the optimizations that I talked about, they can't be solved to optimality, but we did have, in those cases, at least a few days in which to run. The real challenge comes in the bidding systems, especially the reverse bidding process, where there may be 6 or 7 rounds of bidding every day. And so in a round of bidding for a TV station would involve being presented with a set of options. So they may be offered at one price to go off air, a lower price to move to the VHF band, and then the default option would be for them to stay where they are. And every station has a different set of prices, depending on how important they are to the repurposing process. A station out in the middle of a desert isn't going to be offered very much money because you don't need them to go off air in order to repack. But stations in the middle of big cities could very well be offered very high prices. Those prices need to be recalculated 6 times a day for every round of bidding, and all the feasibility checks need to be taken at the end of every round of bidding. And there are 3,000 feasibility checks after every round of bidding. So all of that has to happen on the time scale of tens of minutes.
Okay. You got time for another one between you?
If you're about to solve the same problem in the UK, can you use this algorithm without any changes? Is the scale of the problem, the size of the problem similar?
I think the US is particularly complicated. So I think that not only was this the first time it was done, it was a difficult example that was chosen, and that was because there is no spectrum. A lot of other countries have released spectrum recently through the switch over from analog to digital television. So you can sometimes get a technological windfall in spectrum terms. The US didn't have that available. They were already using digital television. They needed to find another way of releasing spectrum. If this were to be tried in the UK, I think in terms of implementation terms, I don't think it would be any more difficult. The main thing that means it probably won't be applied in the UK is just the nature of the TV broadcast market. It's a lot less complicated. There aren't 3,000 independent license holders in the UK.
Okay. Did you have anything else you want to ask? Go on, Alan, very quick.
I've got a quick parochial one. I'm coming from defence, I know one of the challenges in defence is the military frequencies. Did you have that problem in the US? You talked about radio astronomy, but are there any other protected frequencies or things you needed to work around?
I'm not sure that came up in the broadcast incentive auction, but I'd be happy to talk afterwards if you want to.
Yeah, we'll keep that secret for the moment. Thank you. Can I just ask people in the audience to thank all of our presenters today, because Ian and Sheena, Max and John and Robert,